Welcome back to ch205. In this lecture, I'll be talking about numerical integration. That is section 4.2.1 of the textbook. The first method we're going to look at is trapezoidal rule. As it stands, the rule is coming from calculating the area of a trapezoid. Imagine we have a function like f of x shown in this figure. This is f of x. I have a curve like this. So I have an x as a horizontal axis, f of x is the vertical axis. And my goal is to calculate the area under the curve from x0 all the way to x5. That's exactly mean. So that exactly means calculating the integral of the curve from x0 to x5. Okay, so using trapezoidal rule, what we do is we split this interval into equal intervals or subintervals, and let's call those subintervals delta x. So that means imagine the distance between x0 and x1 is delta x, x1, x2 is again delta x, x2 and x3 delta x, and so forth. So the area under the curve is approximately equal to the area of the trapezoids on the curve. So every ribbon here, let's say this is one ribbon, here is another ribbon, right, from here to here to here to here to here, or from here to here to here to here to here. So every band can be approximated by a trapezoid. The difference between the area of a trapezoid and the area under the curve is actually this is a small sector here, right? So look at how I go along the curve from f1 to f2 and then back from or on the red line to the original point, right? So this little area is the error we're making by assuming that the area under the curve is equal to the area of the trapezoid. Again, for the next trapezoid we do another error, and then for the next trapezoid we do the same or similar error and so forth. So if you just calculate the area under the curve by summing all these trapezoids, or the area of the trapezoid, we're basically making a little bit of error on each, and we sum them up. So the error actually goes up with the area as well. Okay, so let's go back and see how we can calculate the area. Okay, so we know that the area of the trapezoid is sum of the two, let's say, bases. There's one base here, there's another base here. You sum of the two legs, and then multiply by half of the height. Okay? And that's exactly what is here. So this is the first base, or the first leg, this is the second leg, f at point xi, f at point xi minus 1. We get sum of the two, and then we multiply by the half of the height. So this is the height, right? xi minus 1, look at that. So this is x, let's say this is xi, this is xi minus 1, right? The difference between these two is delta x, divided by 2, which will be half of the height. So from here to here, that is the area of the trapezoid. Now we're going to go over all x values from I from 1 to 5. And we calculate the area for each trapezoid, we add them up, because that's what the sigma means, and that gives you the total area. Okay? It's proven using Taylor series that the error that we're making, which as I said, is the area of this little sector that is left out. If you sum them up, it looks like the error is proportional to delta x, so h here is delta x. It's the separation between two successive x values. So the error is proportional, not exactly equal to. It's proportional to the delta x raised to the second power. So we call trapezoidal rule is on the order of delta x squared, or its second order approximation to the integral. Okay, so another way to calculate the integral is Simpson rule. Now Simpson rule is a little bit different. If you look at the trapezoidal rule, we basically add up all these heights and then divide all of them by 2, right? So if you go to the next interval, And for the first interval is f0 plus f1 divided by 2. For the next interval, we have f1 plus f2 divided by 2. For the next interval, we have f2 plus f3 divided by 2, and so forth. So if you expand this sum, you see that trapezoidal rule is going to be something like, let's write it here. So the integral is going to be 1/2 times the first point, which is f0, plus 2 times the second point, plus 2 times the third point, plus 2 times the third point, and so forth, plus 2 times f4. Well, actually, in this case, would be 2 times f4, and then plus f5, and then times delta x. So you see that the coefficients for all f values are 2, right? Except the first point and last point. So the first point, the coefficient is 1. The last point, the coefficient is 1. All others have coefficient 2. Okay, now compare that with trapezoid with the Simpson rule. Simpson rule is a bit different. It says the coefficient for the first point is 1. Coefficient for the last point is 1. Then the even ones, f2, f4, all the way to fn minus 2. The even ones have coefficient 2, and the odd ones have coefficient 4, like f1, f3, and f5, and so forth, right? So again, the very first one and last one have coefficient 1. The even ones have coefficient 2, and then the odd ones have coefficient 4. Then we just get the sum multiplied by delta x divided by 3. Contrast this to trapezoidal rule. The first one is 1, second one, the last one is 1, so far similar to Simpson rule. But all other points have coefficient 2. So here's one difference. Second difference, we multiply by dx divided by 2. This one, in Simpson rule, we divide by 3. Multiply by del x divided by 3. So these are the differences. Alright, so it can be proven that Simpson rule is on the order of h⁴. Right, so that means the error we're making is on the order of delta x to the 4th power. So what does that really mean? That means if you lower your delta x by a factor of 10, that means if you increase the number of intervals by a factor of 10, if you increase the number of intervals like 10 times more, then the error you're making in the area is going down by 10,000, right? Because 10 raised to the 4th power is going to be 10,000. So that's what it means. All right. So here is roughly a proof of how Simpson rule works. Simpson rule is proven by assuming that there is a parabola going through every 3 points on the curve. So let's say the original curve is this one, which is shown by f of x. And I now go ahead and fit a parabola to the first point, the middle point, and then the last point. Between these 3, I fit a parabola. And that parabola most likely is not going to be exactly on the curve. It's going to be this darker line right here in the bottom. Simpson rule says we're going to approximate the curve by this parabola. And then we're going to calculate the area under the parabola. So the difference between the area on the parabola and the function is this little white area right here. And it's proven that this area adds up to about or proportional to the delta x raised to the 4th power. Just to remind you, in trapezoidal rule, we approximate the area by a trapezoid. In Simpson rule, we approximate the area of every 2 ribbons by a parabola. Let's look at one example. So this is example, I think 4.2 of the textbook. I have some x values. I have the f of x values. We want to integrate the function, which is pi times 1 plus x over 2 raised to the 2nd power, and then the whole thing raised to the 2nd power. We're going to integrate it from 0 to 2. So we create a table. So here's a table I create from x from 0 to 2 with the interval of 0.5. Here's the f of x. I can calculate it using Excel sheet. You know how to do that, right? It's pi times 1 plus x over 2, and then raised to the second power, all over raised to the second power. Alright, so this is my f. Now I'm going to calculate the integral using trapezoidal rule. The first point is 0 because we don't have any area under that single point. For the next point, I have to calculate the area from here to here. And the way to do that is we're going to look at the trapezoidal rule. Is the first point plus this last point of this ribbon. We have only 2 points for now. And then multiply by the difference between the 2 points on x and then divide by 2. So that's the area under the current ribbon. And then you're going to add this to the area that we calculated so far on the previous cell, which is C6. So up to now, I calculate the area under the first ribbon, right? We go to the next ribbon. First, we have to add up whatever we calculate for this ribbon to what we calculated before. So that's why we start from C7, which is the area calculated before, right here, the blue cell, and then plus the area of the current ribbon, which is sum of the two bases, right? Which means the green plus the purple, and then times the difference in the x values, which is the height, right? That's the height, and then divide by 2. Okay, so that's the next ribbon. Next ribbon, again, the same thing. We add up what we calculated so far, which is the blue cell, and then times the sum of the two bases for the current cell, which is this plus that, and then times the difference between the x values divided by 2. So we're adding these areas ribbon by ribbon using the trapezoidal rule. And then the last point, you do the same thing. All right, then the last point actually gives you the total area because we are accumulating the area of the previous cell with the current cell, right? So this is the previous cell, and the calculation is just for the current cell or the current ribbon. Okay, so the total area we get at the end of the day is that guy, is 11.98. Let's do it when the h is 0.2. Right now h is delta x, right? It's 0.5. Let's do the same thing now, this time with 0.2, which means we make more trapezoids. Then the area has to go down too, right? Because we make it more accurate. More points, more accurate result. Okay, so my x goes down from 0 to 2 again, but now with the interval of 0.2, you do the same thing, right? Same equation, you can copy paste it here, and I'm going to go over one of them. So that's the area we calculated in the previous cell plus the area of the current ribbon, which is sum of the two bases, and then times the height divided by 2, right? That's the current ribbon. We add up to the previous ribbon, and we go forward. You can just drag it down like that. Okay, and then the end result will be the total area. Now compare this to that. The area has gone down a little bit, right? 1198, this is 1177. Well, this one is more accurate, so that means the error we're making, we can actually calculate how much error we're making if you subtract. Now we know the exact solution for this specific exercise that is given to us, right? The exact result is this, assume, and then if we know that, we can easily calculate the error, which is the difference between the approximation and the error divided by the exact solution, the difference between the approximation and the exact, divided by the exact, times 100, make sure you get the absolute value of the difference. That gives you the percentage error. So with h equal 0.5, the error is about 2%. With h equal 0.2, the error is about 0.3%. So look at that. I lowered the h by almost a factor of 2, and the error has gone down by a factor of 4. Almost 4, right? Maybe even more than that. Maybe 5 or so, right? So that is exactly what I said. Trapezoidal rule is on the order of delta x to the second power, or is the second order. That means the error goes down quadratically proportional to delta x. We lower delta x by a factor of 2, the error goes down by a factor of 4 or less, actually. By a factor of 4 or more, I'm sorry. Alright. Okay, so in the next video I'll be talking about how to calculate this integral using Simpson rule, which is still example 4.2. Alright, thanks all for watching and stay tuned.